So it is, we will have to do calculate now rest of the things. So what is the vertical force here? The vertical force is, with me, right? The F vertical. The vertical force is Q times velocity times B. So here, this is the vertical force, which is QWD. This is the vertical force here. And this Q I can write is, Q will be from here, from this one, lambda DL. DL is radian because it is going along the width. So we have this thing is lambda times A and then W and then B here. While we know that lambda times W, like here, lambda times the velocity is basically the current. So I can write that this is IVA. So the vertical component is this one. And what about the horizontal component? The horizontal component is QUD here. And the horizontal component is equal to QUB. And it's in this direction. It's in the opposing direction. And this is equal to, then I can write this is lambda times E and UB here. Lambda times E UB. And now I do calculate the horizontal one. And look here that in time delta t, the charge moves along the horizontal distance. In time delta t, when it will be dt time, it will be dt time, it will move with W velocity is W dt. This much distance it will move. So the work done, now we are the behind the agent who is moving this thing. Let's say we are having a battery, in a battery or a generator which is presumably moving this charge or increasing this amount of current. Then in time delta t, it will move horizontally by W dt. This much distance is will cover. So I can write that the work done by batteries by a battery is equal to lambda times this, or it will be the force. Which force? Because it is moving that in a horizontal form. So this is the horizontal force, and then the distance that it will move. So the horizontal force here is QUB here, QUB, and this distance is WDT here. So lambda E and UB, this is the horizontal force. So I can write the lambda A UB and WAT is they are perpendicular to each other. So the angle is 9. They are the same direction. It's a dot product. We are in the same direction. So they will zoom. And we have lambda AUB delta T, and then this is equal to lambda EU, lambda AB. If I take this is outside, lambda A and B, lambda A and B, because they are not part of the integral. So I have taken them outside, and here we have U W D T. Now from here we can see that lambda AWB, lambda C, B and W. Lambda AWB is IBA. So we have IBA in the integral. What is left is UET. What this we have? UDT. S equals VT. So we have V and T. So it will give us S. U is this direction. So along this direction, how much it will cover in dt? Is we said that it is H which it is covering, the loop is covering. So this thing comes out to be I, B, E, and H. And this is precisely, if I look at the work done by the batteries, IBAH, this is precisely the work done by the magnetic force. The magnetic force was claiming that I have done this much work, but we came to know that actually the work is done by the battery, not by the magnetic force, because exactly the same amount of work is done by the battery. Who increased the current? The battery increased the current, the source increased the current, and the battery says that I have done this much work. And this is the total work which is done in lifting this loop up. So it means that magnetic force doesn't work. The actual work was done by the battery, but it seemed like the work is done by the magnetic field. So this is one of the very fascinating example that it was showing that the work is done by the magnetic field, but in reality it is done by the battery, because the same work comes up to be done by the battery. And is here we have done the linear current of the current in a line. So what if the current will be flowing on the surface? Then for the surface current, which I call the surface current density, the surface current density, and this surface current density we represent with K a vector quantity. Then the surface current K is basically equal to the current per unit di over dl, which is cross sectional, which is perpendicular. So along the surface we are going, this is a perpendicular length, means the cross sectional length along which this current is flowing. So I can write that current per unit width perpendicular to the flow, and if I define sigma is the surface charge density, means the charge per unit perpendicular length. If I write this thing, usually we say sigma is the charge per unit area, and here this is basically the cross-sectional length along. So the charge per unit area, the sigma, the area here is playing the same role as dm perpendicular is playing here. So I can write that this thing is here implies this K is equal to sigma times V, just like here. So it is the same thing. If I write this charge current is Q over T, and then I multiplied with area over area, then Q over area I will call is sigma, and the length over time, which will remain time here, that will make its velocity v. So I can write k equal to sigma v, and I can do the same practice here. So this is qb cross b, and for dq I will write lambda dl. So accordingly, if I write sigma v for this, then I can write the magnetic. The F magnetic is equal to V cross B, and this is sigma d E. So for dq I am writing sigma dA, because this is sigma, this is dq over dA comes here, so sigma dA will become dq, the magnetic radiation, and then sigma v will come here, sigma v will come here, and then cross b here, and we will have dA here. So sigma v here and sigma v I can write is k. So this will come out to be the magnetic force can also be written is k cross b, and then here write dA. So this is one of the way to represent the current in this form, the surface current in this form. Similarly, I can define the volume, the volume charge, volume current density, and that I represent, this I represent with K, this I represent with G, and J is basically equal to current per unit per particular area, cross section area. So this is current per unit area. Now, if you remember the electrostatic situation, we were writing sigma charge per unit area, and the charge per unit length is lambda. So we are writing it the same manner, but when it comes to current, the current is di or dl, but this dl is perpendicular, is the cross sectional. Similarly, for the volume, we were writing charge per unit volume, the tau that we were writing there, the row, sorry, not the top, but the row we were writing charge per unit volume. But when we write current, then it will be perpendicular area, the cross sectional area that it will be facing. So di over dA perpendicular. And in the same sense as we did here, we are having rho equals charge per unit volume. Now if I write means do the same conversions, like I write this di is q over t, and then this one, the rho I write is q over v, then this is the volume. So this, with the same analogy, I can write is j equals both times v. This v being the velocity of the volume. O times v is I lambda times v. Lambda be the line charge. K sigma times v. sigma being the surface charge, J rho times V, rho being the volume charge. So they are argumenting the same analogy with this. And then we can write is from here, I can write about the rho is TQ over dV, and then this I can write dQ equals to rho dV. dV here is the body, dot is a velocity. So better we write here for this one. If we write this E equal to tau, then this will be much right. So write this is tau. So this will be tau here, rho d tau. Then I can write with the same symmetric equations that J is equal to or F magnetic, means I'm writing F magnetic in this form, F magnetic in this form when P equals to will be equal to here J cross B and V touch J cross B and C touch. So we have some similarities here, and the similarities are that F magnetic is equal to this thing when we were writing it in the form of QV, V being this one. So we have now JD tau, we have GD tau, we have KDA, and we have IVL. So I with DL, K with DA, and J with D tau. So this is very symmetric. Like for example, for charges, I can write summation on I and something here, and then QI VI. Similarly, for these are discrete charges, and then for the line, I can write is expression in IDL. Similarly, means IV a vector here, and for surface, I will write this is K G H, K being a vector, and for a volume or a vessel, this is J and G tau is here. So in the bracket, we are basically having B, the magnetic field. And this is what we are having for the line charge density, for surface charge density, and volume charge density.